Alright, so in this video we are going to learn about uninformed search. So how does search in intelligent systems work? Okay, so people or machines is considered intelligent if he or she or it can find or can search any the solution faster than the other, whether it's the other people, the other machines, or the other system. Then the process of searching the solution that does not use problem domain knowledge usually is known as uninformed or blind search algorithm. In blind search algorithms, all alternatives will be tried to find the solution. So imagine that uh, all the possible options that can lead to the solutions of that problem will be explored one by one to see which one that can give the solutions. Basically, there are two commonly used blind search algorithms. They are breadth first search algorithm or BFS, and the second one is depth first search algorithm or DFS. The difference of these two algorithms lies in the selection of the alternative that will be tried first. Before we go into much detail about this uninformed search algorithm, so let's review a little bit about state space graph. State space graph is actually a tool, a mechanism that we can use to display a representation of a problem whereby every possible alternative paths that will lead to a solutions later on can be explored and analyzed using the same state space graph. So for example here, let's see that we have a false coin problem. So imagine that there are 12 coins, but one of them is false, and the false coin is either lighter or heavier than the original. An ordinary balance scale can be used to determine if any two sets of coins weigh the same or not. Now, our goal is to identify the false coin by maximum or 4 times weighting. So in order to solve this problem, we can first simplify the problem first by using only 6 coins. Okay, so the state space graph example in this false coin problem, we can imagine that we have 6 coins here. This is the simplified version. So imagine here we will have C1, C2, C3, C4, C5, and C6 here. This is the coins that we have on hand. Okay, so this is the state space graph. And then in here, how can we find the solution in this case? So in here, if we want to find the solutions, then we must compare, right? We must compare any sets of coins. We want to compare any set of coin so that we can, until we find the fake coin. So let's see here, for examples, at this time, we want to compare a pair of C3 and C4 with a pair of C5 and C6, right? So here is the state space graph of the coins, the four coins that we have currently on hand. We have 6 coins, and then in here, it is the steps that we take. We want to compare C3 and C4 with C5 and C6. So if, let's say, C3 and C4 and also the pair of C5 and C6, they weigh the same, this is the symbol. If they weigh the same, then what does it mean? It means that these 4 coins, C3, C4, C5, and C6, they are the original coin. There is no fake coin within them. So in that case, it will leave us only with the other 2 coins that we have not compared, right? That we have not evaluate, which is C1 and C2. So in this case, what we want to do here is that we want to compare, take either C1 or C2 and compare with any of the original coin that we have already known. In this case, we can compare C1, either C1 or C2 with either C3, C4, C5 or C6. Let's say in this example, let I pick C1 compared with C3. So if C1 and C3 they are weight the same, the comparison is between these two coins are the same. So it means that C1 must be also the original coin. How can it be that way? Because we already know that C3 is the original coin. So in that case, we know that C2 must be the fake coin. So this is our goal state, right? Our goal is to find one fake coin. Okay, so what if, let's say in this case, let's say actually C1 and C3, they don't weigh the same. So in this case, we can conclude that C2 must be the original coin. And C1, if they don't weigh the same, C1 must be the fake coin. How come? How come it's not C3? Again, because earlier we already know that C3 is the original coin. So this is, we already get two possible solutions from this state. Okay, let's see another possible solutions. Okay, so what if earlier, based on our initial comparisons between the pair of C3 and C4 with C5 and C6, what if the comparison of this pair, they don't weigh the same, right? So if they don't weigh the same, then it's clear that we know either one of C3, C4, C5, or C6 must contain one of the fake coin. And we know that C2 and C1 here must be the original coin. So in this case, in our state space, we can eliminate C1 and C2 because we already know that C1 C2 is the original coin. So in this case, we can take another comparison. Let's say we want to compare the original coin here, C1 and C2, with with the previous pair. Actually, we can choose any of the pair here. Either C3 with C5 or C4 with C6 or maybe C3, C4, C5, C6. Okay, and comparisons of the two pair of coins. Then we will compare it again, similar like what we have done on this left hand side of the tree. Okay, so in here we will yield the comparison of the weight will yield two results, right? There are only two possible results. Whether this pair of coin they weigh the same or they don't weigh the same. Okay, so in this case we have some exercise for you guys to fill in. So please fill in and complete this state space graph of the false coin problem. Please write your answer on the sheet of paper and then later on submit your works on ULS. Alright, let's see. There are also another method to find the solutions using the blind search algorithm. So one of the method is called backtracking. Backtracking is a pretty straightforward way to solve a problem that is to propose any possible solutions and then check if the possible solution, if the alternative that's come up with is constitute to a solution, to a real solution or not. Each proposed solution is called a stage. So each step is called a stage. If all possible solutions in stage I cannot be performed without violating any constraint in the problem set, then we must return to state I minus 1. So this is where the backtracking works. So in case that all the possible solutions in stage I cannot be performed, then we must take a step back, one step backward, right? So this is the so-called backtracking process. So therefore, it says that we backtrack to the previous stage and find the next possible solution within that stage. If there is no possible solution in that stage, then again we continue to step back again, right? We continue the backtracking process again to stage I minus 2. What if in stage I minus 2 we still cannot find any other possible solution? Do the backtracking again. We do further backtracking to stage I minus 3. Okay, let's see an example of this backtracking process in the egg queens problem. So the egg queen problem is that we are asked to place egg queens on an egg times egg chessboard so that no two queens are attacking each other, or there are no two queens occupying the same row, same column, or diagonal on the board. So for example here, let's say this is the queen number 1, this is queen number 2, and queen number 3. We can know that there is no other queen, right, on the path of queen number 1 here. Let's see this one. Let me mark it for you guys. Okay, there are no other queens that can be placed on the path of queen 1, whether it's vertically, horizontally, or diagonally. So the same also be said to the queen number 2, right? There should not be any other queen on the path of queen number 2. So this represented by the orange line with this one, right? Okay, the same also apply for queen number 3, this one, right? So there are no other possible queen that should be placed, whether it's vertical, horizontal, or diagonally, right? So to solve this problem using backtracking, again, this will yield a very complex alternative, right? If we want to solve it using backtracking. So in this case, we can just take a step back a little further by simplifying the problem that we have. Instead of directly finding the solution for egg queens, let's simplify the problem into the four queens. So the same problem, four queens on the 4 by 4 chessboard. Okay, let's see. Here, this is our I equal to 1, right? This is I equal to 1. Okay, so we place our first queen over here on row 1, column 1. So this means that we cannot place any other queen on the board that is marked with red line here. Okay, finish. We go to stage 2. The value of I equal to 2. Again, let me give a mark over here. So this mark shows that there should be no queen placed on the chessboard marked with the red line here. Okay, so let's say the second queen is placed on row 3, column 2. So in this case, there should not be any other queen later on to be placed on the one marked by orange and also red line. This one, so it should be this one. Okay, so in this case, we know that when the value of I equal to 3, in this case, we cannot place any of the queen on the column 3, right? Why? Because all column number 3 here actually been marked by the line. So in this case, no matter the where we put our queen next, let's say here on row 2, column 4, then we cannot place the fourth queen. So in this case, since we cannot do so, we must step back. We must take a little step back from stage I equal to 3 back to I equal to 2 here. Okay, we do the backtracking here. This one. Okay, let me write it. Backtrack to I equal to 2. In here, in I equal to 2, we change where we place our second queen. So let's say here it is changed not in row 3, column 2, but we change to row 4, column 2 to become like this one. Okay, so let me mark it again for you guys. In this case, we should not put any of the queen over here, right? So in this case, we can place the third queen, let's say here, again, if I equal to 3, we can place our third queen over here on row 2, column 3. Whereas from here, we will know that later on, we cannot put the fourth queen. Why? Because actually this one, row 3, column 4 is within the move of the queen number 3. So in this case, we must backtrack. Okay, backtrack. Okay, we backtrack this step to I equal to 2. So it means that we cannot put our second queen over here. We also at the same time we cannot put our queen over here, right? So this state shows this one, I equal to 3. So since I equal to 3, no matter whether the move that we put over here cannot lead to any possible solutions, right? So in this case, what should we do next? We backtrack 2 steps. Okay, we backtrack here. If I equal to 3, still cannot make the move, right? Backtrack. This one I equal to 3. The same move we can make any other move. Backtrack to 2. This one backtrack I. This one I equal to 2. Since in I equal to 2 here, no matter what kind of move that we will make later on, we cannot come up with solution. So we must backtrack again at this step. Right? So we backtrack over here and then to become I equal to 1. In I equal to 1, then we can freely choose where we want to put our first queen here. So in this case, let's change our first queen to row 2, column 1. So in this case, it's clear that we know we cannot place uh, the other queen on the cells marked with the green line here. Alright, so this is exercise for you guys. Please complete the state space graph for the 4 queens problem previously. Again, continue. You can write your answer on a piece of paper and then later on submit it on the ULS. Alright, next. So how we can use TFS to solve 15 puzzle? So remember here, TFS stands for tap first search. So let's see what actually the 15 puzzles problem is. So the 15 puzzle problem is that we are given a puzzles the size of 4 by 4, so in which it has in each tile inside the puzzle it contains a number starting from 1 to 15. So imagine then the sequence within the puzzles are in a jumbled state like this one. The sequence is random, so our goal is that we must make these 15 puzzles to have the correct sequence like the one on the right hand side this one. So the number should be listed in the order sequence ascendingly from 1 to 3 up all the way to the 15, and we are only given one blank state. Right. So in this case, there are some other versions of these 15 puzzles, such as the 8 puzzles and also the 3 puzzle problem. Okay, so again, let's see if we want to solve this problem. So we can just take the simplified version of this problem because it will stand the same, the step by step. Right. So here's the thing that we must be aware is that the state space for solving the puzzle it can become very large depending on the size of the puzzles. So the state space that is required to solve the 15 puzzles is 16 factorial, which is it's a 2.9 multiplied by 10 exponent of 13. So there are these 2.9 multiplied by 10 exponent by 13 possible arrangements to find all the possible solutions, all the steps and also the possible solutions. However, in real world, a search from the start state to a close state usually will not take that much amount. So usually it will only need half of the number of these 16 factorials. So for example here, let's say we want to use DFS to solve the 16 puzzle problem. Right. So in this case, let's see. Remember when we want to solve this problem, instead of we move the number tile one by one, which really leads to many kind of state space. So we just want to consider moving the blank tiles. So we only want to move this one, the blank tile. Okay, and then the order of the movement, we are only load of up, down, right, and also left. Okay, up, up, down, right, and also left. The search process is blind, but here, so that we won't create any meaningless search space, state space. Okay, so here is the constraint that we have. We will avoid repeated states. For example, after we move the blank tiles up, the next move that we cannot choose down. Why? Because it will return back to the initial state. Okay, and then for each forbidden move, it will not generate the state space. So for example, from the start state in the previous slide, blank move cannot move right. So for example, in this one, from the start state here, the blank space, it cannot move either to the right or to down. Right. So let's see how to solve these three puzzles using TFS. Right. So you can see here, this is our start state, this one. Alright. So we move this blank space to up, right? So the TFS here is we will dig down deeper on the child that has been created first before we explore the other alternative move that can be generated from this one. So from this state here, we know that we can make two moves, right? Up and left. But here we generate the up move first, so we will not consider the move to the left. Right, so this is one of the way in the FS. Okay, so moving up, the playing tiles move to here positions, and then next from this state, okay, from this stage, what are the moves that we can make? Up, down, right, and left. Right, move up, we cannot move up because it is a forbidden move. Right, forbidden. At the same time, we also cannot choose move right. Why? The same reason, forbidden. Right. So in this case, we can only move down or move left. However, in this case, what will happen if we move down? Well, it will return back to here, to our initial condition. So we should not choose this move down. So even though here, we still must generate the state space, but we will not expand this state space for the next iteration. Okay, so we don't choose move down. We go back here, go back to the parent state. Okay, and then from here, we can only explore the other alternative is that we move left. Okay, so we move left. Move the blank dash here to the left, this one. From here, obviously we cannot move up. Move up is forbidden. Move left is also forbidden. So we can only move down. What about move right? We cannot move right, right? From here. Because if we move right, it will return back to the this stage, to the parent state. So in this case, we choose move down. After we move down, this one, again, since we are using the FS, so we will explore the possible solution for this child. So we move up here. If we move up, we can move up, but we should not choose this one. Why? Again, because it will return back to its parent state, this one. It will not generate any solution at all. And then the next one, move down. Move down cannot be chosen. It is a forbidden move. And then how about move right? This one, we can move it to the right. So we get this state. How about move left? Moving left also forbidden move. Alright, so from this stage, we can only move up or move left. Again, similarly, we cannot move left. Why? Because moving left will just return back to its parent node. So we choose to move up. Alright, we move this blank space up, and then from here again, we can just move. We cannot just move up, but we just move down here. Should not be chosen. Right? We can only move to the left. From moving left, we can only choose move left. Move down. Sorry. So from move down, we cannot choose move up. It should not be chosen. So we are only left with move to the right. So we get the goal. This one, we get the goal set here. So the algorithm of depth first search is that we will search through the generated time first before we explore the other possibilities. Alright, let's see another examples of solving the problem using depth first search. So in this case, we will take a look at the missionaries and cannibals problem. So the missionaries and cannibals problem are the common and general problem with correct tables in which we are tasked to move the three missionaries and three cannibals from the east bank of the river to the west bank with a raft. The raft can hold no more than two people, and at least there one person is needed to move the raft from the whether from the east bank to the west bank and vice versa. Right? And also there is another constraint that we must be aware of is that the number of cannibals on any bank can never outnumber the number of missionaries. Otherwise, the missionary will be eaten. So, or in other words, it will be game over. So in this case, how can we represent the knowledge of this problem? Okay, so in this case, we know that we can represent the knowledge for this problem using these notations. The state in the West Bank, the number of missionaries and cannibals in the West Bank, comma, the number of missionaries and cannibals in the East Bank, and also the position of the raft. In here, we can use a flag, we can use a code, right? Let's say 0 means the raft is located on the West Bank, and 1 means the raft is located on the East Bank. And then from here, we also know that there are only 5 possible moves. We can either move 2 cannibals, move 1 cannibals, move 1 missionary, 1 cannibals, move 1 missionary, and move 2 missionaries. So find the solutions of the missionaries and cannibals game using depth first search. Okay, so we will continue to solve this one using the state spacecraft. In this case, this is our initial state, this one. Right, this is our initial state. So from here, we can move 2 cannibals from the east bank over to the west bank. So in this case, we will left with this state. On the west bank, we have 0 missionaries, 2 cannibals, and then on the east bank, we have 3 missionaries, 1 cannibals. And the rough positions from the east bank is located on the west bank. So from this state, what are the possible moves that we can make? We can only move either 2 cannibals from the west bank to the east bank, or move only 1 cannibal from the west bank to the east bank. So this is the only move that we can make. So in this case, Let's see what will happen if we choose move to cannibals. Right, we cannot choose this one. Why? Because it will lead us to the same condition as our initial state here. Okay, so this should not be chosen, and then in that case, we can only move one cannibal over from the west bank to the east bank. So we will get this state. So from this state, again using the fs, what can we do? We can either move one cannibals back over again from the east bank to the west bank. However, we should not choose this one. Why? Because it will return back to the parent state here one. This one. At the same time, we can also move two cannibals over here from the east bank to the west bank. It's possible. Or in this case, let's say we move only one missionaries, one cannibals. So can we do that? If we move one missionary, one cannibal, of course we can move one missionaries, one cannibal over here. However, what will happen here is that if we move one missionary, one cannibal here, let's see in this case, where the number of missionaries is lesser than the number of cannibals on the west bank. So this should spell as a game over. So the move should not be selected. Okay, and so on and so on. So this is how this the solution finding, solution search using TFS works. Okay, so let's do another exercise here. Please complete the TFS state space graph for the cannibals and missionaries problem here, and please write your answer on a piece of paper, and also uh, later on you will need to submit it on the ULS along with the previous two exercises. Next, let's see how we can implement the TFS algorithm into the coding, right? We just learned all about the theory. Now we want to implement it. So the various search algorithms they can be used to list. The first list is open list and the second one is a closed list. Open list contains all nodes in the tree that are still being explored or expanded. Meanwhile, a closed list contains the nodes that have already been explored and are no longer under consideration. So in depth search, the search moves deeply into a search tree as quickly as possible. So here is the keyword for TFS. The search will move deeply into the search tree as quickly as possible. So that's why every time it generates a child node, it will we will go to the channel and then generate the other channel for that until we find no possible move that can be made from the child nodes. Right? So it means that the newest added node in the open tree must be explored first. So this kind of behavior can be facilitated using stack. So remember the stack structure. So one of the characteristics of the stack structure is that it has the last in, first out or LIFO mechanism. So, so stack data structure is much more appropriate to be used with TFS. Okay, let's see how it works. How we can trace the TFS algorithm. So imagine that we have the following state space graph. Okay, so the initial state is A is the start position, right? And then we want to move from A to G1. G1 is the goal here. So how can we trace the route from A to G1? Well, as a human, we can directly see it's clear as a day, right? From A, B, E, G1. But how can we make the computer be able to find the route from A to G1? Okay, so remember the explanation in the previous slide. We need to use two lists. One is open list and another one is closed list. So in this case, we in the first step we will put the starting node in our open list. In this case, A, we write it down. Okay, and then the closed list that we have, this one, this is closed list. Okay, and the first step here, we don't have anything in our closed list. It is an empty list. Okay, so what are the next steps that we must do? We must explore this one, right? We must explore this node A. So we put node A here from our open list into our closed list. And then from A here, we got B and C. Okay, from A, we got B and C. So we put both B and C into our open list. So here is how DFS works, right? So what is the first node in our open list? B, right? So remember, when we want to add the nodes into the open list in DFS or BFS later on, we will always put the left child first. The left child will be put first, then the right child. Okay, this is the left child. This is the right child. Okay, left child will be put first before the right child. Right. So from A we got B and C. Okay. So from here we put B and C here, and then next we want to move our P here from the open list, from our open list to our closed list. So from A we move to the P. Okay. So from P here we know that there is another two nodes D and E. So we put D and E in front of our open list. Remember the characteristic of stack, last in, first out. Okay, so we put D and E in front of node C because we want to go deeply into the search tree as fast as possible, right? So in this case, we put D and E in front of C, and then again, we want to explore D here. We put D from our open list, we move it to our closed list. Okay, from P to T, we will get I and J. So we put I and J in our into our open list. So right after we uh, input our these two nodes I and J here, we want to expand, right? So we move the node I here from open list, we move it to our closed list. Okay, we move here, but unfortunately here we know that there is no other child node of node I. So in this case, what we must do here, never mind, we don't explore, we don't add anything into our open list, we just add I into our closed list. So the next step, what we will do is that this is the illustrations, right? So we don't have any child node in I, so it means that we go back here to the parents. The parent here is D, right? So from D here, we know that we have another child, J. J is in front of our open list. So here we move J into our closed list. Okay, we move J into our closed list. And then we also know that J actually does not have any other child node. So that's fine. In our open list, we are left with E and C, right? We don't add anything because J does not have any other child node. So in this case, let me change up to another color, this one. Okay, so in this case, we must go back again, back to the D, but we know that T here, node T, does not have any other nodes, right? Does not have any other child nodes. So in this case, we must go back again to the parent of T, which is node P. Okay, in node P, we know that we have another child is E, right? This E is actually in our located at the front of our open list here, right? So now we want to explore node E here. So here we go to E, okay? So we move E from our open list to the closed list. We got K and G1. We got K, this one, alright? And then we move K from our open list to our closed list here. Unfortunately, K is not a goal, and then K also does not have any other child nodes. So what we must do is that here we go back to the E. We know that E has one other child called G1, right? So right after we move K to our close from open list to the closed list, then we know that we have found the goal here in our open list, in which G1 is actually located at the first at the frontmost of the of our open list. So in this case, we have found the answer. So how do we respect the answer? So again, we can respect the answer from G here. We can know who is the parent node of G1. The parent node of G1 is E. And then who is the parent node of E? It is P. Who is the parent node of P? It is A. So we get the solution is A, B, E, and G1. So this is how to trace back the the nodes, right, in DFS algorithm. Right, so let's try to trace the DFS algorithm. Let's say here G1 is not the goal, but G2 is actually our goal. So what will be the open and close list in the DFS algorithm will looks like later on. So please finish write down your answer on a sheet on a piece of paper, and then again later on you will need to submit your answer on ULS along with the previous 3 exercises. Okay, so let's move to our next topic here, breadth first search, BFS. Okay, so the BFS that we are going to learn here is known as the breadth first search. So please be careful not to confuse it with some other BFS algorithm. There is some other BFS algorithm called best first search which use heuristic. However, in the breadth first search for the uninformed search algorithm, it does not use heuristic at all. Okay, remember this is a blind search algorithm. It does not use any heuristic at all. So in here, for breadth search, you can find some solutions in the given problem. So each node in the problem set will be visited level by level, starting from the top to the bottom in the left to right order. So for example here, traversing the following tree using PFS, let's say from A, B, C, D, E, F, G, it will produce first, we will travel from top right. Let's say this is level 0, this is level 1, and this is level 2, right? So we start from A. So from A, we expand what is the child node of A, right? We write this one, A. And then from A, we know that it has 2 child nodes, B and C. So we got B, this one, we write B. After we know there is B, A actually has some other child, right? Some other possibilities called C. So we move this one. We write C because C is also the child of A. So from here, from level 1, we move back. We go back to the next level, right? Move back to the next level here. Actually, we go back to what is the child node of B? This one, right? The child node of B, we will know that we will have 2 nodes D. We write D, right? And then next, we'll get E. Right, so from here, we know D and E are the child node of B. So from here, again, 2 on the same level from left to right. So from E here, actually we know that there is node F, which is the child node of C. So we write F, and then next we write G. So this is how BFS works. Okay, let's see how to solve the 3 puzzle problem using BFS. So in order to solve these 3 puzzles using BFS, so again, please remember that we will only move the blank tiles, and the only possible move that we can make is up, down, right, and left. So in this case, from this state, we can only either move up or left, right? We cannot move down or right. Why? Because it is a forbidden move. So moving up here from our start phase, okay, let me write this is level 0, level 1, level 2, level 3, and this is level 4. Okay, so from level 0, from this one, our start set, we go down here, moving up of the bank space, we get this state. And is there any other possible alternative solutions for from this start space? Yes, there is. So we move it. There is some other nodes, right? We can move this blank space to the left. So from here we get this one. So from here we know that from we can expand this one, this node. Actually we can expand it to become another two nodes here, another two states. We can move it down or left. Okay. So if we move it, let's put it this way, right? So we move it down here. We know it is moving down, but this is we cannot choose this move. Why? Because it will reflect back to the parent node of this P. So we got to this one moving left. So the 3 is moved, and then we go to the next options of this state C. In state C here, we can move it to the up. We get this one, and then if we move it to the right, let's say we move it right, we also should not do it this way. Why? Because it will reflect back on the parent node of this node C. Okay, let's say here, from here, we know that we still have not found our answer yet, right? So we moved on another level, this one. So we expand. Now we will not expand this one, as this will yield the loop. Okay, so we expand the next one. Next node here is this one. It will have two child, right? We can either move down or move right. So if we move it down, then we'll get this one moving down, and then if we move it to the right, this one. However, we will not choose this one later on. Why? Because it will return back to the parent state of this node E. Again, we choose the other possibilities. We follow up from this node. We can either move down or move right. Right? But we will not consider this one, and move right we consider this. So from here to level 3, we move down. Okay, to some other possibilities here that we got. We move from the child node of these nodes is we can move either up or right. But we won't choose up because it will return back to the parent node. So we go the other direction is move right. Okay, so this one we will not explore. This one we also not explore, right? So from here, the last node in level 3 here, actually it has two possible, two alternative other child nodes, right? So in here, we start to select it can move either down or to the left. So if we choose down, it moves down. So voila, actually we find our goal here, right? But if we choose left, it should not be chosen. Why? Because again, it will refer back to the parents of this state space. Alright, so since we already found our goal here in level 4, so we don't need to expand the other possibility from this node or this node. Let's see how we can solve missionaries and cannibals problem using BFS. Okay, so consider that this is our initial state of missionaries and cannibals on the west bank and east bank. Alright, so we move, let's say if we move one missionaries. So we move one missionaries from the east bank to the west bank, this one. We cannot choose this one. Why? It will spell game over because the number of missionaries on the east bank is lesser than the number of cannibals. And then the other possible move is that we move from here, we move two missionaries over. However, we also should not spell this one. Why? The number of missionaries on the east bank is only one. Meanwhile, the number of cannibals is three. So it will spell game over for us. So the other possible move that we can make is that we can move one missionary, one cannibals from the east bank to the west bank. This one. Or we can also move only one cannibals from the west bank to east bank. This one. Or we can move over two cannibals. This one. Right? So if we move two cannibals, then after this we can expand on the next level. Okay, since we will not expand this one and this one, so we'll directly start from this one, from this state space, this one. So from this one we can only move one missionary, one cannibals, or one cannibal. Right? What if we move one missionaries? So it will become in this state. So it's still safe on the East Bank. Why? Because the number of missionary here is larger than the number of cannibals. What if I move one missionary, one cannibal over from the East Bank to the West Bank? Sorry, from the West Bank to the East Bank. Well, it cannot be done because it will spell a loop. It will create a loop similar with our initial problem again. So what if I only move one cannibal over? So in this case, if we move only one cannibals over, so the number of cannibals on the east bank is more than the number of missionaries on the east bank. So it will spell game over. Okay, we already explored all the child. Uh, okay, so we have already explored all the child solutions, all the possible solutions from this node. So we get back to this one. So let's say here, zero missionaries, one cannibals, two missionaries, two cannibals. So what if I move one cannibals over from the west bank to the east bank here? We can do so, however, we should not choose this way. It will spell loop, right? So what if for the next part here, for the next part, we move we move one cannibals over. So we become zero missionaries, one cannibals, three missionaries, two cannibals. However, we also will not choose these solutions. Why? Because the solution is actually the same with this one. And then let's see what if we move two cannibals over, so it will return back to the initial state. So here, please continue the state space graph of this problem until you find the goal state again. So please do it on a piece of paper and write down your answer. Later on, please submit it on the ULS along with the previous 4 exercises. Next, how can we trace PFS algorithm? Earlier, we have done the tracing of the FS algorithm using open list and closed list. So now, if we want to trace the PFS algorithm, again, similarly, we must use the help of two lists, one open list, one closed list. Okay, so we trace back one by one here. Okay, so given that either G1 or G2 is the goal, starting from A, right? So find the route to either G1 or G2 from A. So in here, we will write down A in our open list, and there is no nodes at all in our closed list. And then we move this node A from our open list to the closed list. And then we fill in what is the child node of A, B, and C. Remember, we will always write the left child node first before we write down the right child node. Okay, remember, we will write on the left child node first before we write on the right child node. So in this case, in our open list, after we expand node A, we will write node B and C inside our open list. So from here, again, the algorithm of VFS, we will expand A, B, and C, this one, right? We will expand the left child node first, this one, in which, in this case, B. So B, we will expand it and put B into our closed list. So we will get D and E. So next we will put this D and E behind node C, because BFS, it used the queue characteristic first in first out. So obviously any new nodes that that will be explored later on, the child node of an explored node will be put at the end of the previous node inside the open list. So that's why in here, in our open list, C move to the front of the list, and then after C we'll get D and E, in which both D and E are the child nodes of B. Okay, so next, what we want to do here is we want to expand node C. So we move C to our closed list, so we will get G2 and F in our open list. Okay, so from here, what we want to do here, we know that from uh, from B we already get two child nodes, right? T and E, which were expanded first before we expand the child node of C. So in this case, okay, we must expand node T, sorry. We put node T here from our open list to the closed list, and then we will get I and J, node I and J. This node I and J, we will put it at the back of our open list. Okay, and then next we want to expand node E, this one, because E is located at the front of our open list. We move node E, this one, from open to our closed list. Then we'll get G2, F, I, J, and G1, K here. So in this case, please be careful that we actually have already found our goal state here. We already found G2 here. Since either G1 or G2 is the goal state, so we don't need to find all the other G1 and G2. We just need to find either one, so we find the goal. So from here, we know that G2 is the goal, so we can trace back from G2 to see the root. Okay, so the parent of G2 is node C, right? So from C, we know that the parent node of C is node A. So in here, the solution that we got is A, C, and G2. Okay, let's see, this is our last exercise for this meeting actually. So let's say that given the same tree as previously, however, neither G1 nor G2 are the goal. However, N, this node N, is the new goal that we must find. So please write down, trace the tree using BFS algorithm, starting from this A, until you find node N. So please write down the state of open list and closed list similarly as the previous slide here. Write down your answer on a piece of paper, and again submit all your answer with the previous exercises on the QLS. Alright, I think that is for our today's topic, Uninformed Search, and see you again in the other video.